Okay, so we grab class 2 and class 2.dat. Are we all set? Ready to go? Okay. So now we have the hypothesis that the effect across time is not linear, but the effect is somehow curvilinear or quadratic. And in regression, how do we look at a quadratic effect in regression? What do we do? We just square it, right? We're going to do the exact same thing here. The nice thing is we also would like to be able to test one model against another, and this is what makes, in regression, if you want to test whether or not adding a quadratic effect affects your model, how do you test that? What do you do?
Hierarchical regression.
Okay, hierarchical regression, and what are you looking for?
The incremental R squared.
Yeah, change in R squared, right? And now change in R squared, if you have a significant change in R squared, then you can say that it significantly improved your model or at least significantly increased the variance accounted for. Unfortunately, with quadratic effects, a lot of times you'll actually get a significant quadratic effect in regression and an incremental change in R squared that's very minor, right? That may or may not actually be statistically significant. Which makes it difficult to make a case for adding a quadratic effect. The same thing is true in latent growth curve modeling. Unfortunately, we have a way to test that because now we're using structural equation modeling. And how do we test something in structural equation modeling? We can use a chi-square difference test, right? So let's set this up and let's initially look at our model here using these, and I'm just gonna open up some data here. I'm gonna open up data set 2. Oops. All right, so in this data, I just restructured it a little bit so that each person has time 1, 2, 3, 4, and they have time listed here. And let's look at our data. We're going to scatter time by t. I actually did that wrong. Okay. So we have data that looks like this, which is difficult to look at, but it's all nested at time 1. Or I mean, it's all nested within each time point, right? And if we had like a perfect linear effect, then we would see something that looks roughly this wide, right? Increasing all the way across, right? But we don't see that. We see something else going on here. And it looks kind of like a fan or a funnel, right? And this is oftentimes what we see when we start observing quadratic effects. We see things, we see a dispersion of data that starts to look funky. And we talked about this in ARM 2, right? When we would do our scatter plots in ARM 2, and I would say, okay, so this looks like we don't have good homogeneity of variance and what's going on here. And there was a few different options. One of those options was that it was a nonlinear relationship, right? And so we can test for these nonlinear relationships by adding a quadratic slope to our model. But first, let's just test a simple linear model. So we have time 1, time 2, and time 3. We're doing something like this. We have an intercept, and a slope. One, 2, 3. Let's run this. Let's see how our model fits. We've got some issues, right? So first, residual covariance is not positive definite as it should be. There's a problem with time 3. This model looks like garbage. That's because when you make up data to fit a specific type of model, it looks like garbage. Everybody else's look like this as well? All right, so for the time being, let's do this. Our chi-square is 334.067 with 5 degrees of freedom, okay? Somebody can remember that? We can remember 334 and 5, that's easy enough. We are going to come in and we are going to add a quadratic slope. Now, we could do this one of two ways. We could do something like this. We can go I by, and then fix each one of these to 1, right? S by this, and then S, or let's just say Q by, that would be 0, that would be 1. What would this number be? What did we do in regression? 4. And this one would be 9, right? We're assuming that time, that this is actually a predictor, right? Like if you look in here, in this data set, when I've restructured it, I restructured this as time, and time is now a variable with values of 1, 2, 3, 4, right? And in fact, if we do something like this, mixed t time ID, oops, oh, little baby ID. We're going to get something like this. It says our constant is minus 2.55 and our slope is 2.575. And whoops, if I open this back up, no, I don't want to Skype with anybody today. If I open this back up, class 2 out, what did I say let's look here, minus 2.55 and 2.57. This is not going to be perfect, and we'll talk about why it's not perfect, but it should be pretty close here for our intercept and slope. Well, at least for our slope, 2.131. The reason that the intercept is actually off. So I had 2.131, and in here it's 2.57. Why are these numbers not quite right? Let's try this. Those look a lot closer, 2.57 and 0.01, 0.03, or 0.3. The reason that they're not quite right is that it's twofold. In the first one, my intercept was actually not even in the model, right? It was 1, 2, 3, 4. But when we're doing this as a latent growth curve model, it's 0, 1, 2, 3, right? And so my 0 value is actually outside of the data set. It's just continuing to plot that line backwards to give me an intercept that winds up being minus 2 in this case. But the other reason that we'll talk about in 2 weeks is because I'm doing a multi-level model right there what I was doing in Stata. But in M+, it uses the latent growth curve model, and in Stata you get a single random variance component, but in M+, you have a residual variance for each time point, right? We'll talk about that. That's the special case. I said that multi-level modeling is a special case of latent growth curve modeling. You don't need to worry about this right now, but that's the special case. It's when all of these residual variances are held constant at some sort of value. Doesn't matter, although maybe I'll show you later on today how to make those exactly the same. But regardless, so we set these things like this. What else do we need to do in order to make this work? We need to have, what did we do before when we made this work? Remember, if we run this right now, actually, if we run this right now, it'll converge, but we won't get any information on the intercept or the slope, right? We won't know what the intercept is. We won't know what the slope is, and why is that?
Oh, you gotta set one of those to 0.
Right? We've got to go back. We've got to set these things to 0. Now, unfortunately, I kind of messed something up here. But okay, so we have to actually go T1 through T4 at 0, right? And then we also have to ask for ISQ. I didn't test this at home. Hopefully this doesn't go completely wonky on me. Model estimation terminated normally. What was our chi-square before? I think it was 324. And what were our degrees of freedom? I think it was 5. So we've lost 4 degrees of freedom, and our chi-square has dropped by, let's call it 323. Is that significant? 323 for 4 degrees of freedom? Yeah, that's you can look that up, but you don't need to look that up. Here's our correlations with our intercept and our slope and our quadratic slope, and here are our mean effects. Our intercept is 0.521, and what is 0.521? That is going to be what? The average where? And which one was set as 0? It's time point 1, right? So let's go sum t if time equals 1. It should be close to that, 0.516. It's not going to be perfect, remember, because it's linear regression. That's pretty close, right? But yeah, it's the average. It's still going to be the average at your 0 group, which is time point 1 in this case, right? All right. And what does our slope tell us? That across time, we see an average increase of 1.035. And what does this tell us? Yeah. So that means that across time, what does a positive quadratic effect tell us? You know what? Let's do one better. Let's open an Excel folder. And let's build a graph for this. So we have ISQ, and I was what? 0.521. What was S? Can somebody just look and tell me on your screen? 1 point what? Nobody wants to tell me? Fine. 1.035. Oh, you guys didn't get a chance to get it all plugged in? I'm sorry, we'll go back to that. All right. So we have time, right? And then we have time squared. And so this is, actually, let's not do that. We're only going to have one slope, right? And this was 0.512, or 521, I'm sorry, 0.521, wasn't it? Equals this times this. Are we following? Are we tracking here? Plus this times it should be this, but it won't let me click in there, so I'm going to click here. Then I'm going to change this to C3 times C3 again, right? Hello. Plus this. Make sense? And now we have to come in here and change these things to be dollar sign, dollar sign, dollar sign, dollar sign, dollar sign,
What
dollar
does it mean when you
sign.
put dollar sign?
It means when I hit enter, it won't go down.
Oh, okay.
Yes, and so then we move this here, this here, this here, right? Everybody tracking? Who's not tracking?
Can I see the formula?
Ah, that's what happened. Something happened. I was like, why is this looking weird for me? There we go. All right. So now we want to put this into a chart, right? Some sort of a graph. Go.
So what does the X represent? Does that represent like the new value after the effect, the change, or?
That is actually it's our predicted value, right? It's a predicted value. So if we go like this, I think this is what we want to do. Then we go insert. Where's my chart? Oh, let's just go. Where are charts at? Insert. Oh, here we go. Okay. Line charts. Oh, I didn't need this one, actually. This is our slope, right? And you can see it's not quite linear. And I like to do this fun thing where we format data series. Make my line smooth. And actually, if we extend this out, let's say 5, 6, 7, we grab this and we pull it down. And then we grab this. It's easier to see how this effect becomes quadratic, right?
Mm-hmm.
So this little piece right here is saying that for every 1 unit increase, this slope speeds up by 0.521, right? That's what a quadratic effect is. What if this was negative? What would that be doing? Yeah, I mean, we can just, right? And our intercept doesn't change. And we get this kind of weird thing where it's like, initially it seems like it doesn't even look like it goes up because that first one, it drops so dramatically. But anyway, that is how you graph a quadratic effect. If you have a quadratic effect, it's easy, it's quick, it's simple to just throw a graph in there. And sometimes these effects look really cool. Like, so for example, if this quadratic effect were actually much steeper than what it is, oh, that didn't change it that much. Can I make it really steep? Oh, it's just changing this value. Oh well. I was trying to get it to be, every time I change it, it's just changing the x value so that it doesn't look that steep across time. But okay, anyway, that is how you graph your quadratic effect. Yeah. Does everybody understand why we did C3 times C3 here? Yeah, it's because it has to be time squared, right? And so in order to get the effect of the quadratic, the x variable for that is the squared time. If you remove this, what happens to that line? Yeah, it just straightens out, right? Remove it, pull this down, the line goes straight. All right, does that make sense to everybody? Back to our model. We can see that our intercept at our 0 point is 0.521, our slope is 1.035, and our quadratic effect is 0.512. So that means at time point 2, what should our intercept be?
Would it be 2? Or no? Like 2.07?
Let's have a look. Where did you get 2.07?
I added the intercept plus the slope and the quadratic change.
Okay, let's have a look.
Probably incorrect.
Let's have a look. So we have -1, 0, 1, 2. And what is this going to be? What's -1 times -1? What's -1 times -1? 1.
Oh, -1.
0, 1. What is this going to be? 4, right? Let's have a look. And our intercept is,
Oh, nice.
yeah, right? It's just simple math. It is simple linear algebra, adding, subtracting. Yeah. So now everybody understands how he got that, right? I just want to make sure. What is the intercept going to be at time point 3? Just of note here. This is why this is important. If we go sum sum caps lock is on. Sum t if time equals 2, 2.08751, right? It's fairly close. Of course, it's perfect if you use just the coefficients that it's giving there because it's simple linear algebra adding coefficients, right? What is our time point going to be at time point, or what is our intercept going to be at time point 3? Oops, I shouldn't have done that yet. Who wants to grab their calculator and tell me? Time point 3, the intercept should be what? I'll grab my calculator.
4.7 or something like that.
6, 8. Yeah, that's a pretty good guess. 2.0 without adding or without. 0.512. I'm getting like 4.639. Give it a try and see what happens. Anybody get anything different than that? All right. So we have now -2, -1, 0, 1. What is -2 times -2?
4.
-1 times -1? 4.639. That's what I got, right? I mean, it's just simple addition or subtraction, whatever. So that's saying that as our slope increases, or as we move from time point to time point, our slope is going to increase by X amount, and it's going to accelerate, right, by 0.512. By every 1 unit, it will accelerate by that much. Your slope will get steeper. All right. Does that make sense to everyone? Everyone feel comfortable with that? Everyone knows how to now graph that by plugging in that equation? Yeah? Um, Now, of course, M plus knows that people like to look at quadratic effects the same way they like to look at just plain linear effects. So it gives you an even easier way to do this. ISQ. I grab this one. And it is 0, 1, 2, 3. And so you can do IS just like this. Save, run. It's the same way that we did it last time, right? This should not fit good. It should fit like garbage because we have data specifically saying fit like garbage. Remember, we had 334 and 5. It's exactly the same model, right? And then if you just throw a Q in here, M plus knows what you mean. If you want to go beyond this, beyond a simple quadratic and look at a cubic effect, unless M plus has changed, we can look at this in a second. I believe you have to make it manually yourself, the way that we just did with quadratic, but then you could name it something else. But let's scroll down here, 1 degree of freedom, 0.475. All of these things fit exactly the same as they did before. These all are exactly the same. So M plus says just throw a Q in there and you're good to go. You know what? Let's see if C works. I don't think that C will work, but it did. That was a complete guess. Let's make sure that it's actually cubed. I mean, it did cube them, right?
Oh, nice.
Wait, yeah, 2 cubed is 8, 3 cubed is 27. This data does not have a cubic effect, obviously. Could test it kind of like this in M plus, or I mean in Stata. We could just go mixed, new time. Let's see what Stata says about this. Stata will converge. That's interesting because Stata says that there is a cubic effect. Oh, but this is weird. Our standard errors never change. Oh, that's why. Hold on a second here. Yeah, no, actually there is not a cubic effect, right? 0.777. If we dump one of these, yeah, we have significant quadratic effects, and those numbers look pretty close to what we were getting before, right? Slope of 1.03, an intercept of 0.523, and this here, let's go back here and let's have a look at, so if we're going to look at our quadratic effect again, the things that we were looking at before were the correlations between the intercept and the slope, and the main effects of the intercept, the slope, and the quadratic effect. And then we had one other thing that we were particularly interested in, right? Which was the variances of these things. And so we see that A, not everybody's starting off in the same spot, right? We have significant variance in where people are starting. We have significant variance in people's slopes across time. And we have significant variance in the degree to which people accelerate or don't accelerate, right? All right.
When we tested the cubic relationship, I know that we did that for fun, but when I tried it here, I didn't get. I only got the regression coefficient, not the standard error, the p-value, or any of that. Is that what you got too?
Well, for the cubic effect, the model didn't converge.
Oh, is that right?
Yeah, it should look like garbage, right? I mean, let me throw it in here again. I do think that's cool that you can just throw C in there.
And we just want to look at
I mean, my guess is you could actually put any letter in there that you want. I don't think that I, S, and Q actually mean anything.
Oh,
I
it's
think
like
it's the
number.
place. Yeah.
Okay.
But this is what it looks like, right? Like model, it says terminated normally, but obviously it didn't. There's all kinds of issues. Yeah. So this, I would conclude that it's just like not. You know what? Let's see what happens.
This will work.
You already tried it?
No, I just guess it. And it will be a good model.
Oh, it won't work.
Just for data.
Yeah. This did nothing. So let's see what it says. Number of fixed time scores is not sufficient. Oh, because we only have 4 fixed time scores, we don't have enough to go beyond that. You wind up having an oversaturated model, right? So anyway, that is quadratic latent growth curve modeling. Do we have any questions over that? We are good to go there. Perfect. Let's take a short break, and when we come back, we will finish up by talking about, what was the last one called? I mentioned it in the thing, and now I can't think of it. No, we're not going to talk. We'll talk about dual process. Oh gosh, I don't know. I'll have to look it up when we're on break. I can't remember. That's stupid. I can't remember the name, but I can tell you how to do it. We'll come back after break and we'll go through it.